Hi, my name is Joseph Defendre, and this is my presentation for CS330, for CS5330, Classical Vision Topics. My assigned topic is number 103, the concept of the normalized cut versus the minimum cut, and why it's useful for segmentation. You see, to a computer, an image isn't just really a scene, it's just a giant grid of colored dots or pixels. So this is the very first thing an AI has to do to stop it from seeing a picture and start seeing it as a network of connections, or what mathematicians like to call a graph. So let's dive into that. This whole transformation, going from pixels to connections, is the absolute foundation. It's how the AI gets the image ready for analysis and turns all that visual data into a structure it can actually understand and work with. So how do you build this network? It's actually pretty intuitive when you break it down. First, every single pixel in the photo becomes a point. We call it a node. Then we draw lines or edges to connect the nodes, and connect the nodes that are close to each other. But here's the really key part. Those connections have different strengths. The more similar the two pixels are, in color or how close they are, the stronger their link. So a blue pixel right next to another blue pixel, that's a super strong link. But a blue pixel next to a red one, that's a very, very weak link. Okay, so we've got our network. Now what? The whole goal is to find the boundary between things. The most direct way to do that, and what's the most direct way to do that? Well, just find the weakest bunch of connections and break them. This brings us to this big idea of a cut. A cut is basically just the total price you have to pay to break all the links separating one group of pixels from another. You can almost think of it as a breakup energy. You need to split the image into two distinct parts. And logically, this makes a ton of sense, right? The boundary between two different objects, say your face and the wall behind you, that boundary should be made up of really weak links. I mean, your skin tone is way different from the paint color, right? So a good separation, a good cut, would be a cheap one. It should just follow the path of least resistance. And this super simple logic gives us our first hero of the story, the minimum cut algorithm. Its whole mission is just beautifully simple. Search the entire network and find the absolute rock bottom cheapest cut you possibly can. Seems perfect, right? Find the weakest boundary and you find the object. Case closed. But as it turns out, this clean and simple, elegant idea has a huge problem. It has a tiny but absolute fatal flaw that keeps it from being the perfect tool we need. Let's just pause on that for a sec. I mean, what could possibly go wrong with finding the path of least resistance? The absolute weakest boundary in the whole image. Well, here's the thing. The minimum cut algorithm only cares about one thing, the cost of the break. It has zero concept of the size or the importance of the two chunks it's creating. And what that means is that it has this massive bias for finding like a single lonely pixel or a tiny meaningful little speck that's kind of different from its neighbors and just lopping it off. So this is the core of the problem. You see, the minimum cut's goal is just too simple. It'll find the cheapest cut, sure, but even if that cut just isolates some useless little island of pixels, what we really need is a smarter way, something that looks for a cut that's not just cheap, but also balanced, meaningful. And this is where our new hero enters the scene, the normalized cut. It's a much smarter version of the minimum cut that introduces one crucial new idea to the mix: balance. Now, to get that balance, we need a new concept. It's called association. Just think of it as a way to measure how big a segment is, not just in pixels, but in its total connection strength to everything else. It basically tells us how significant that group of pixels is, so a big cohesive object will have a really high association and a tiny little speck, a very, very low one. So how does the normalized cut use this? It's simple, but it's totally brilliant. It takes that same old cut cost from before, but then it divides that cost by the association of the groups it's creating. In other words, it's adjusting the price of the cut based on how big and important the resulting pieces are. And what does adding this one tiny division step do? Well, it changes everything. In short, it punishes imbalance. It basically puts a huge penalty on any cut that produces one massive piece and one tiny insignificant little speck. Okay, let's just walk through why this is so clever. Imagine an algorithm is thinking about cutting off one tiny little pixel. That simple pixel has a super small association value, right? So when you take the cut cost, which might already be pretty small, and then divide it by that tiny association number, boom, the final score becomes massive. The algorithm sees this giant penalty score and goes, whoa, no way, and just learns to completely ignore these silly unbalanced cuts. Now, one important practical detail. It turns out that solving the normalized cut exactly is actually an NP-hard problem, meaning there's no efficient way to try every possible partition. So how do we actually compute it? The answer is a technique called spectral relaxation. Instead of solving the hard discrete problem directly, we relax it into a continuous generalized eigenvalue problem. We build an affinity matrix W, which holds all the edge weights, and a degree matrix D, which sums up the connections for each node. Then we solve the equation D minus W times Y equals lambda times D times Y, and the second eigenvector of this system gives us a soft assignment of pixels to groups, and we threshold that eigenvector to get our final segmentation. This is what makes normalized cut practical and computable on real images. And that brings us to the main takeaway. When you're trying to teach a computer to see objects like a human does, just finding the weakest boundary, that's not enough. It turns out balance is everything. So let's just put it all side by side one last time. Minimum cut, its strategy is to find the cheapest boundary, period. And the result is that it often just cuts off tiny, useless specks, but the normalized cut is strategy. Its strategy is to find balanced groups by weighing the cost against the group size. And the result, it actually finds whole, meaningful objects. And that's really the core of the lesson here. To see the world intelligently, an AI can't just look for the easiest, cheapest divisions. It has to look for the ones that create balanced, significant whole things. So in the end, it's not about the cheapest cut at all. It's about the most meaningful one. Thanks for watching.